this discussion will focus on something known as a Popov Criterion. So this is a criterion which again deals with the feedback interconnection of a LTI CISO LTI system. We'll talk at least with respect to a CISO LTI system and a memoryless nonlinearity that lies in the zero k sector where k is a finite positive constant. Okay, so uh, this pop-up criterion is specifically seen in case where the loop transformation that is done is such that the transformed nonlinearity that we get is not a memoryless nonlinearity. In such a case, we get a transfer function, a transformed transfer function. And then the condition that we get is actually on something known as the Popov plot of the LTI system G. Okay, and hence the name the Popov criterion. So consider the nonlinear system, which is basically a feedback interconnection of the LTI system G. We'll consider a single input, single output system LTI system. So CISO LTI system G and memoryless nonlinearity psi, where the nonlinearity belongs to the zero k sector, and k is, as I mentioned, a finite positive constant. Okay, so please note that in this feedback interconnection we have y to be equal to xi and the input u to be equal to minus phi. Okay, so we had done some loop transformations that we had to for circle criterion, so that we can take a memoryless nonlinearity in any sector to the zero infinity sector, and then accordingly we transform the LTI system G so that the feedback interconnections becomes equivalent of the original feedback interconnection that we had. Okay, so here what I am claiming is the feedback interconnection that you see between something known as the G bar, which is given in the dashed blue box, and psi bar, which is given in the dashed red box, is same or is equivalent to the original system, which was a feedback interconnection between the LTI system G and the memoryless nonlinearity psi. Okay, now please note here the transformation that we have is resulting in a nonlinearity which is not memoryless. Okay, so what we will first see is whether this transformed system is equivalent to the original feedback interconnection or not. Okay, so how is the memoryless nonlinearity transformed to this psi bar? So the output of the memoryless nonlinearity is multiplied by k inverse, where k is the same k as is used in the definition of the sector in which the memoryless nonlinearity psi lies. What we do is we add this to the input that we get to psi bar, and the input to the memory based nonlinearity psi bar is denoted by xi bar. Okay, and the output of this summation is essentially passed through a filter which is given by 1 by as plus 1, where a is a positive constant. It's a finite positive constant. We pass it through that, and the output of this is xi1. Now, similar transformation is done on the LTI side. So we multiplied the input u by k inverse and pass the output of g to a transfer function as plus 1, and add both the outputs to get y bar. Okay, now to have this interconnected system in figure 2 to be equivalent to figure 1, we need to be able to show that if we start with xi1 equal to xi as an input to the memoryless nonlinearity psi here in figure 2, once we traverse the entire loop, we'll see that the output of the transfer function block, or the output of the filter 1 by as plus 1, will be xi again. So if you start with xi, travel the entire loop and come to the same point where the output of the filter is again xi, then it shows that this is same as what we have. uh, this is equivalent to the original feedback interconnection. Okay, so let's start with the fact that xi1 that you have in figure 2 is nothing but equal to xi. If xi is the input to psi, then the output phi1 is nothing but phi. And then from the figure, it turns out that the input u1 is nothing but minus phi, and hence the output y1 is nothing but xi. Okay, so as having established this, if we look at the block, y1 is the input to as plus 1 and we get y tilde. Okay, and please note that y1 is equal to xi, so y tilde can be expressed in terms of xi as a xi dot plus xi. Okay, now y bar is an addition of y tilde and k inverse u. Okay, k inverse u1, with the fact that u1 is minus 5. So we have u1 to be equal to minus 5, and y bar is the addition of y tilde to k inverse u1. So that gives me y bar to be equal to a xi dot plus xi minus k inverse 5. Now this is what we call as xi bar, that acts as the input to the memory based nonlinearity psi bar. Okay, now to this xi bar we add k inverse phi to get xi tilde. Okay, and this xi tilde is what, from if we see the expression of xi bar and add k inverse phi to it, we get xi tilde to be equal to a xi dot plus xi. So we have a system whose input is xi tilde, and the output xi is such that the xi bar is equal to a xi dot plus xi. This is same as representing it through a block where xi bar is the input to the transfer function 1 by as plus 1 and the output is xi. Okay, so what we get back is the output of the filter 1 by as plus 1 is going to be xi if we start with the fact that xi1 was xi. Okay, so when we travel the entire loop, what we got is the same signal back. Okay, so with the same signal back, since the g with the assumption that xi1 will be equal to xi, we got back that xi1 is indeed xi when we cover the entire loop. So this system in figure 2 is equivalent to the system that we have got in figure 1. Okay, so now since we have established the equivalency, if the origin of the system shown in figure 2 is asymptotically stable, then the origin of the original feedback interconnection shown in figure 1 will also be asymptotically stable. So we'll focus our discussion on to the figure 2 now. Okay, so what we will now try to establish is the memory based nonlinearity psi bar and the transformed LTI system G bar, both of them are passive. If we can establish this, then the feedback interconnection of G bar and psi bar will have an origin which is asymptotically stable. Okay, so the origin of the system figure 2 is asymptotically stable, then the origin of the system in figure 1 is also asymptotically stable. But now we need to establish, as I said, that G bar and psi bar are passive. And okay, in addition to that, I need to establish that G bar is strictly positive here so that I can establish asymptotic stability. Okay, so we'll start with the establishment of psi bar being passive. So let us look only at psi bar. Okay, so if the notation, I have slightly changed the notation here. So now xi1 is the input to the system psi bar, which we earlier represented as psi bar. So I'm sorry for any confusion that arises. So let me correct this actually. So I'll say this is xi bar and everywhere where xi1 occurs, I'll be changing them to xi bar. So xi bar is the input to the system xi bar. So if we see the system xi bar, what we have is a xi dot plus, so from this system what we have is a xi dot plus xi minus 1 by k phi will be equal to xi bar. Okay, so xi bar is a signal which is nothing but a xi dot plus xi minus k inverse phi. Okay, this is what you have. With this, if you add 1 by k to it, you'll get a xi dot plus xi. Okay, so from the expression of xi bar as the input, what we get is a xi dot to be equal to this particular value with xi bar as the input. Okay, let me change xi1 to xi bar everywhere so that okay. So from the expression of xi bar, what we get is a xi dot is nothing but equal to this, where psi of xi is nothing but phi. Okay, because xi is the input to the nonlinearity psi and the output is being represented by phi. Okay, so this is what we have. Now notice that since psi is a sector nonlinearity lying in the sector 0 to k, where k is a finite positive constant, we have this relationship to be true. So the integration of psi sigma d sigma over the interval 0 to xi, okay, is always going to be positive. This is positive definite. Okay, this function is is a positive definite function of xi. So if we take a Lyapunov function for this nonlinearity, let's say it's v psi. Psi is in the subscript to denote that we are taking it for the nonlinear part as a scaled version of the integration that we had. So we take the Lyapunov function to be equal to a multiplied by the integration of psi sigma d sigma over the interval 0 to xi. So this is what is the Lyapunov function. Now if you take a derivative of this, v dot is nothing but a psi of xi dot. Now psi of xi is nothing but phi, and xi dot's expression is a xi dot expression is already given in here. So we substitute this a xi dot expression, and what we get is this. Now if we consider everything in this expression other than the xi bar psi of xi term, what we have is the remaining expression to be less than equal to 0. So v dot is equal to xi bar multiplied by psi xi plus something which is less than equal to 0, then we can safely say that v dot is going to be less than equal to psi of xi multiplied by xi bar. Okay, now psi of xi is nothing but phi. So phi is the output of the nonlinearity psi bar. Okay, so if we consider the nonlinearity here, which is psi bar, the input is nothing but xi bar and the output is phi. So what we have established is the Lyapunov function associated with the nonlinearity psi bar is such that the rate of change of the Lyapunov function v dot is less than equal to the input and the output product. Okay, and this is the relationship that establishes that psi bar is essentially passive. Okay, please note that we are considering a memoryless nonlinearity psi which lies in the 0k sector. Now since we have established psi bar, we are left with the fact that we need to ensure g bar is strictly positive real. If we ensure g bar is strictly positive real, then it would mean that g bar is also passive, and hence the feedback interconnection can be established to be asymptotically stable. Okay, So if we see the expression, then G bar is nothing but G multiplied by 1 plus S added by K inverse. Okay. Now, for G bar to be strictly positive real, the right half of the S plane, which means the imaginary axis and everything to the right of the imaginary axis, should map to, or rather, should be such that G bar lies only in the first and the fourth quadrant. Okay, strictly in the first and the fourth quadrant. Okay, that is what we have said, that for all s as that real part of s is greater than or equal to 0, the real part of g bar of s must be greater than 0. Okay, so another way to prove that this is strictly positive real is to show that g bar is Hurwitz, and for s equal to j omega, the real of g bar j omega, for s equal to j omega, the real of g bar of j omega is positive. Now, for if you look at the expression for g bar is Hurwitz if gs is Hurwitz. Okay, because the denominator of g bar is same as the denominator of no, sorry, because the poles of g bar are the same as the poles of g in this particular case. Okay. Now, with so what we need to start with is a G which is already full. So whatever we are discussing is for a G which is already full. Okay. The next part that remains is to find a condition such that for s equal to j omega, real of g bar j omega is positive. So g bar, if we substitute the expression of g bar j omega, what we get is that we need to ensure that this relationship holds for all omega greater than equal to 0. This holds for all omega greater than equal to 0. Now, the inequality here that we see is basically represented by a region that lies below the straight line that passes through that lies below a straight line, and the equation of the straight line is nothing but this, where x is real of g omega, gj omega, and y is nothing but omega times imaginary of gj omega. Okay, so this is where we come to the Popov plot of the LTI system GS. In case of a polar plot or a part of the Nyquist plot, what we plot is real of gj omega with respect to the imaginary of gj omega, roughly speaking. Okay, so the polar plot is between the real of gj omega, and imaginary of the gj omega. But in Popov plot, the plot is between the real of gj omega, which you see here, and omega times imaginary of gj omega. This is what is known as the Popov plot. Okay, if you plot for omega greater than equal to 0, the plot that we get for real of gj omega versus omega times imaginary of g omega is known as the Popov plot. Okay, now the inequality that we have got is essentially satisfied if the Popov plot of the LTI system GS lies below the straight line given by x minus ay plus 1 by k equal to 0. So if the Popov plot of GS lies below this green straight line, then which is described by a that appears, that is a filter coefficient that we have, and the k that is because of the sector in which the membryless nonlinearity lie. Okay, so if the Popov plot of G lies below this green straight line, then it would ensure that the inequality is satisfied, and for s equal to j omega, real of g bar j omega is going to be greater than 0. So we already have g bar to be Hurwitz if g is Hurwitz, and with the satisfaction and once the Popov plot lies below the straight line, we have that G bar is going to be um, strictly positive real. Okay, so now notice that just for a greater than 0 and k greater than 0, the resulting memory based nonlinearity psi bar is already passive. Okay, so for the feedback interconnection to be for the feedback interconnection that we had to have a origin which is asymptotically stable, we need the Popov plot of G bar. We need the Popov plot of the LTI system G to be below the straight line given by x minus ay plus 1 by k equal to 0. Okay, when the memoryless nonlinearity is lying in the 0k sector. This is what is known as the Popov criterion. So, for some psi belonging to the 0k sector, if the Popov plot of GS lies below the straight line x minus ay plus 1 by k greater than 0, where a is the filter coefficient used in construction of the memory based nonlinearity and k is the maximum slope that represents the sector under consideration. In such a case, the feedback interconnection of the LTI system G with the memoryless nonlinearity psi has a asymptotically stable origin. Now, since this result is based on the Popov plot of LTI system G, this result is known as the Popov criterion. So this result essentially tells you how to look into a feedback interconnection in case you transform it to be a memory based nonlinearity using a first order filter. So we'll stop here. Thank you.